Welcome back, everybody. I still haven't had a chance to take care of this recording. I will be posting this one here. This is a very, very good example of trying to prove continuity or find places of discontinuity of a piecewise function. So be on the lookout for that. I'm going to try and record that later today or tomorrow. Just need to make sure I remind myself. And if you don't see it up by tomorrow, if anybody could please just send me an email saying, Phil, you're a liar and a beezy, as kids say, and you should be ashamed, so that I can make sure that I actually upload it on time. So we had a couple more that we wanted to do here, specifically this one. I love this question. So find constants a and b such that the function below is continuous everywhere. So the function is the constant function of 7 when x is greater or less than 1. It's equal to a cosine pi x plus 2bx when x is between -1 and 2. And then it is equal to 5 when x is greater than or equal to 2. So in a similar fashion, if you look at each piece individually, that's the first step when determining whether things are continuous or not. Each of these functions, so a and b are just numbers. A and b are just numbers, so that middle piece is continuous everywhere on its interval. So there's no real issues on any of the pieces themselves. The main issue that will arise is at the dividing points. So we need the limits to exist there. So we need the limits as x approaches 1 from the left of f of x to equal the limit as x approaches 1 from the right of f of x. We need that to be true. If we're approaching 1 from the left, we're going to be the first function, right? We're going to be in function number 1. So let's go ahead and find those off on the side here. So the limits as x approaches 1 from the left of f of x, that's just the limit as x approaches 1 from the left of 7, which is 7. Do you need to be this eccentric about it? Absolutely not. You can go straight from here to here. I am fine with you doing that. I encourage you to do so. I'm just showing it for completionism. Just showing you the full details of what's going on. Saying that, okay, we're approaching 1 from the left, so our function is going to just be replaced, like our function is going to be 7 there. Similarly, the limit as x approaches 1 from the right of f of x, that'll be the limit as x approaches 1 from the right of a cosine pi x plus 2bx. And I know what you're thinking. How do I handle this? This has 3 variables in it. It's impossible. No, it's not impossible. A and b are just numbers. We don't know what they are yet, but they are numbers. They don't depend upon x. So in the limits scope, those are just constants. So we can ignore them and just write them down. So this becomes a cosine of pi times 1, which would just be cosine of pi, plus 2b times 1, which would just be 2b. Or more aptly, negative a plus 2b. And so we need these two things equal. In order for the limit to exist, right? Because what do we need for continuity? We need 3 things. We need the function to exist there. We need it to be that the limit exists there, and then we need them to be equal. Now, we don't have enough space to do those first and third options, like showing that the function exists there and that the limit are equal. But suffice to say, as long as we do this, we'll be fine. And we can, I'll explain why in a little bit. So we have that going for us. And we need that the limits as x approaches 2 from the left of f of x is equal to the limit as x approaches 2 from the right of f of x, the other dividing value. So we need the other dividing value to have the limit be correct. So we'll just compute those. And we don't have much room, but the limit as x approaches 2 from the left of f of x, that would be the limit as x approaches 2 from the left of which function? Middle or bottom? If we're doing the left, we're going to be the bottom function. So a cosine of pi x plus 2bx, and we'll plug in 2. And cosine of 2 pi is 1. That's right back at the right side of the x-axis. So this will be a plus 4b. And the limit as x approaches 2 from the right of f of x, that's just going to be 5. And we need these equal. Are there any questions on that? So far, rather. So to reiterate why I'm doing what I'm doing, I need this function to be continuous everywhere. That's the main goal. That's the end goal. So we saw each piece separately and saw that they were going to be fine. They were all going to be okay. Because remember, we had that theorem that says that all functions are continuous on their domains. Like every function that we encounter, they are continuous as long as they are within their domains. And cosine is defined everywhere. X is defined everywhere. So each piece is fine. The only issues are the dividing values. And so for that to happen, we need to make sure that the left and the right hand limits agree piecewise. And so we found the left and the right hand limits, and we need these two things to be equal to each other. So, well, how does that help? I've got 2 equations and 2 unknowns. So this gives me negative a plus 2b is equal to 7. And it also gives me a plus 4b is equal to 5. System of equations. Bet you didn't think you were going to have to see those again, right? We did them once. We did them a little bit in 126. And then said, whatever, we don't need to worry about it anymore. No, it will come up again and again and again. If your goal is to take Math 182, there is a section called partial fraction decomposition, which will require you to solve systems of equations. In 283, you start talking about how to solve, find critical values of multivariable functions, which will sometimes entail solving systems of equations. So this never goes away. Linear algebra is what this is like. The field of studying systems of equations. Linear algebra never goes away. It's one of the most important fields of mathematics because it's found everywhere. But either way, we can solve it however we want. If you want to do substitution, you can. I don't know why you would, because we have a perfect setup right now to just add down. We can use elimination, but that being said, we use the substitution method or any other method that you've learned with how to solve a system of equations. I am just going to add straight down, which will allow us to cancel the a's. And so we get 6b is equal to 12, which tells us that b is equal to 2. And then we can use either equation, the first one or the second one, the negative a plus 2b is equal to 7, or the a plus 4b is equal to 5. We can use either one to solve for a by plugging in 2 for b. So I'm just going to use the first one. So negative a plus 2 times 2 is equal to 7. That gives me negative a plus 4 is equal to 7. So negative a is equal to 3, which gives us a is equal to negative 3. So a is equal to negative 3, b is equal to 2. Any questions on that? And it's okay if there are. That's a challenging problem. Really fun, right? Super cool. That to bust out some of our preliminary knowledge about solving systems of equations. Grabbing everything. So I really like this problem. Now, technically speaking, what I should do, if I want to prove continuity there, I would also need to check to make sure that the like with these values of A and B, that f of 1 exists and is equal to 7, and f of 2 exists and is equal to 5. But that's a little bit that's going over the top. Okay. The intermediate value theorem, very, very, very important theorem in mathematics for a lot of reasons, but not really for ones that we need to use. I'm just going to briefly mention it. So this is why continuity is so important. It allows us to have things like the intermediate value theorem, the extreme value theorem, and in some ways the mean value theorem later on. Suppose f is a continuous function, and without loss of generality, assume that f of a is less than f of b. So like the first value is down below, second value is up higher. If k is any real number between f of a and f of b, then there exists at least one c value such that f of c is equal to k. So instead of actually doing a problem with it, I just want to show you the intuition. So imagine, so let's just say here's A and here's B. And so our curve looks like this, the quintessential calculus curve. Wait, let's change that just a little bit. Actually, I'm just going to go like that. So that's f of x, right? So up here is f of b, down here is f of a. And so what the intermediate value theorem, that's a continuous function. It's a nice curved line. There's no breaks in it. There's no removal of discontinuities, nothing like that. So it's all good. So what the intermediate value theorem is telling us is that if you have a k value between f of a and f of b, let's just pick it right here, then there has to be some value between A and B. There has to be some value such that f of c is equal to k. And that's what it's telling us. The most important implication of this is that if on one side of a value, like if at one value you're negative and at one value you're positive, then there has to be a point where you cross the x-axis. Which intuitively, it kind of makes sense. If you're drawing a nice curve, right? It would have to cross the x-axis at some point, but that's how you can use it. That's one of the most important implications. The other one that's kind of another implication, which is what we were using a lot in the background whenever you were solving nonlinear inequalities, is that in between zeros, the function has to stay positive or stay negative. It doesn't magically jump around. So, but you're not going to be tested on the intermediate value theorem. It's just a fun little extra thing. And that completes unit 1. So that's all about limits. And then that means we'll never see them ever again. Lies. There's a reason why we study limits in the first place, and I'll explain it once we get there. Now, I also mentioned I updated, it took me a second to update the homepage, but I have updated it with the exam 1 review. But keep in mind, the exam 1 review, I need to edit it and a little bit with my exam 2 review, but either way, the exam 1 review only has unit 1 material on it. There's only unit 1 material, but our exam 1 covers unit 1 and section 2.1, and you'll see why once we actually start talking about section 2.1. So for section 2.1 for the exam, I highly recommend looking over the unit 2.1 exercises as your study guide. There's some very, very good problems in there, but without further ado, we will now go to the guided lecture notes for section 2, which is on the derivatives. Derivatives, very fun. Very, very fun. So we'll start with just what it means to what the derivative is. Then we'll talk about all its fun rules that it has. And then at the very, very end of our section, we will learn about related rates, which is a very, very fun application problem. So, starting off with the definition of the derivative. This is actually one of those things that give you a little bit of a history lesson. So everyone says that Newton is the inventor of calculus, right? Especially if you listen to Neil deGrasse Tyson, he's like, and then he invented calculus. And that is true. Newton did invent calculus, but he didn't do, but there was another person who invented it at the exact same time. I think, if I remember correctly, his first name is I'm just forgetting his first name. His last name is Leibniz. I need to know right now. I need to know. I'm sorry. Sorry, guys. We have the power at our fingertips. Gottfried. Way off with an Andrew in it. Gottfried Leibniz, very, very famous mathematician as well. And the way that they invented calculus was actually very different. Newton was thinking about it in a certain way, and Leibniz was thinking about it as a completely different way as well. Now, Leibniz wanted to actually collaborate with Newton, but Newton was like, nah, screw off. I don't want to deal with you. And that actually caused some big problems in Europe. Since Newton was England's golden boy, they followed his definition, whereas everyone else followed Leibniz's. And the way that Leibniz described calculus was actually far more intuitive and allowed for the rest of Europe to get far more advanced in mathematics before England ever did. So Leibniz's way was way more intuitive and led mathematicians to a deeper understanding of what the derivative was. But either way, they both came up with the same concept, just in different ways. And then there's also books that try to teach calculus in the way of Leibniz, which is very confusing, but it does work out in the end. Either way, the way we start off, we typically follow Newton's way because it's a lot more intuitive at first. At first, it's very, very nice. Once you start trying to discover higher degree mathematics, that's when Leibniz's way is better. But either way, if you guys remember from Math 126, the idea of a secant line, which is where you take 2 points on a curve and connect them, and that's representing the average rate of change. Like if you were to use it in a real world context, like finding your average speed on a road trip. Like you travel 5,000 miles or whatever over 60 hours, what's your average speed? So the way you calculate that, if you remember, it's m subsecant is equal to f of b minus f of a all over b minus a. And the thing that kills me about this whenever I teach Math 126 is like students they get freaked out by it, but all it is it's just the slope formula. That's all it is. F of b is your function value at x equals b. F of a is your function value at x equals a. So you've just got y sub 2 minus y sub 1 over x sub 2 minus x sub 1. It's just the slope formula, just written differently. So in comparison, we have the concept of a tangent line. So that is a line that locally, not like it doesn't have to be everywhere, but it only touches the curve at one spot. Instead of being 2 spots and connecting the line, it is a line that touches it exactly once. And how do you determine the slope of such a line? How could you do it? And therefore, if you have the slope, then you also have the equation. So this is where the concept of limit comes into play. So imagine if you have a and b here. So then this is f of a, and this is f of b. And we see that this line is a secant line. Okay, screw you. That's fine enough. So it's pretty close to being tangent, like only touching it once, but it's not. But if I were to make them closer together, so notice that the space between them has gotten smaller in the second picture. Here's A and here's B. Here's f of a. Here's f of b. And we see that we've got a slightly, like there's a little bit of line issue, right? There's a little bit where that you can see, if we zoom in super far, it's touching it twice, but it's getting better. And finally, if I were to make A and B virtually indistinguishable, we would see that we have a line of tangency. And so that's how we're going to use the concept of the derivative, right? We're going to make A approach, we're going to make B approach A. That's what we're going to do. We're going to make that, we're going to take the limits as the B becomes A. So let f be a function. Then the derivative of f, which is denoted by f prime of x, so that the way we say this is f prime. So the one line there is we call it prime. So f prime of x, and is defined as f prime of x is equal to the limits as h approaches 0 of f of x plus h minus f of x, all divided by h. That is one way to write it. The other way to write it, which is the way we kind of use to describe how it works, is, so I'm going to put this kind of in side note land, or the limits as t approaches x of f of t minus f of x all over, oh, wait. How do I want to do this? I don't want to do this. There's a lot of different ways you can write this. And I am, yeah, this will be fine. T minus x. F of t minus f of x over t minus x. We're going to be using the left one almost exclusively. So we're going to be using this is the better one. That's the much better usage for us. As I've said in kind of the note here, the first option is the preferred formula when computing derivatives, whereas the second version is far more useful when dealing with proving things for abstract functions. And you might be wondering, like, well, how are these the same thing? And just imagine if x is some, or if h is some positive number, right? It could be negative too, but as it's approaching 0, it's going to be a number that's slightly larger or slightly smaller than your value a or whatever. And so as h goes to 0, that x plus h will become x. So one way we could write it, instead of like this a and b here, and this is where a lot of textbooks would write it, this is x, and this is x plus a little bit more, x plus h. And as h goes to 0, x plus h becomes x. So as h goes to 0, this value goes to x. So it's the difference quotient. That's the reason why in Math 1.6 we have you do it at all, is to just kind of give you some practice with inputting f of x plus h. Now we talked about that in detail, remember? This is f of the quantity x plus h. You're plugging x plus h into the function. You're not adding h at the end. And so the other note is that this is describing the derivative at any value of x. So this is how you would find the overall function that you get from taking the derivative. If you want to know at a specific value, you would just replace x with a. So for example, if I wanted to find the derivative at 5, So f prime of 5 would be the limits as h approaches 0 of f of 5 plus h minus f of 5 divided by h. Or it would be the limit as t approaches 5 of f of t minus f of 5 over t minus 5. However you want to do it. But we're going to primarily stick with the first way. In terms of some mathematical jargon, just so that we don't make the it just hits the ear wrong, at least from a mathematician's perspective, is we are taking the derivative. We are performing differentiation. We are not deriving the derivative. So we're not going to say that we're deriving it. Deriving is a different word. So it's taking the derivative, differentiation. Just to, so we don't say deriving. We're not deriving the function, because deriving the function would mean like creating the function, not taking the derivative. There are many different ways that the derivative is written. F prime, that's Newtonian. That's the way Newton described it. So f prime of x. Leibniz used a concept called infinitesimals. He said dy over dx, which is another way to write it. And to talk about Leibniz notation in just a second, I'll mention other ones. Some people also write capital DF. But these are the main two ways. F prime and then dy dx. Another way to write it is d dx of f of x. And so d dx meaning take the derivative with respect to x. So we'll talk about that in a little bit. But one thing that's important to talk about is dy dx. Dy dx. That looks like it's a fraction. It's not technically a fraction. It can be thought of as a fraction sometimes, and that's actually the reason why the rest of Europe got so much got much more advanced in mathematics than Europe did, is because they thought of it like a fraction every once in a while, and that allowed them to discover new things. But dy over dx is not actually a fraction, so you can't just magically break it into pieces. Just as a little bit of an important note, the thing that's representing, do you guys remember, like have you guys seen this notation before, delta x? Have you seen that notation before? If you haven't, delta x is meant to mean a change in x. Delta y would be a change in y. And so what Leibniz discovered, and this is what you'll see in this picture here, is that when you get to this stage, we're talking about, like over here, we're talking about delta x, a small change in x, and then delta y would be that small change in y. This small change in y over this small change in x. That's what the secant line is. And so what Leibniz was discovering is, what if we made that change, that delta x, what if we made that infinitesimally small? So an infinitesimally small change in x, and an infinitesimally small change in y. So he used a concept that he called infinitesimals. That's what dy and dx are representing, is what he called infinitesimals. So an infinitely small change in y divided by an infinitely small change in x, which is a slope, a rise over a run, a change in y over a change in x. But he's doing it at an infinitely small level. And that's what that notation represents. And that is the reason why we can't treat it like a fraction. At the end of the day, at face value, is these are not numbers. These are infinitely, like we're dealing with infinity, like we're dealing with infinitely small things. And so because of that, we can't necessarily treat them like fractions. You can every once in a while, just to prove stuff, and then you ignore the rules for a little bit. But point being is that the reason why it's called dy dx is because he's making this delta x, this change in x become infinitely small. So either way, key fact number one when it comes to finding the derivative by the definition is that we're not done simplifying and therefore cannot take the limit until the h in the denominator has been canceled. We are not done, and there will always be what? Yes. We're not done simplifying. When? That is not a valid English sentence. We're not done. Yes. Thank you. We're not done simplifying and therefore cannot take the limit until the h in the denominator has been canceled. We need and the fun fact is that with everything we'll see in this course, there's always a way to cancel it. So you can rest easy if this problem shows up on any quiz or an exam, that you know that it's not the Yang-Mills existence and mass gap problem. It's not one of the Hilbert 50. Hilbert's a mathematician, created 50 or so, and not by himself only, but Hilbert was a great mathematician who created a bunch of problems. He postulated a lot of things. And so they're called the Hilbert problems. And some of them have been solved at this point, but other ones are still unsolved to this day. And they're called the $1 million math problems, because the mathematical societies would give you $1 million if you figure it out, which isn't that much money anymore. But back in the 1960s, it was a big deal. $1 million is still a lot of money, but either way, for the amount of fame that you would get for solving these things, you're basically you become a giant in mathematics. There's a mathematician at the University of Los Angeles, UCLA, Terence Tao, if you've ever heard of him. Very, very important mathematician. He figured out the twin prime conjecture, which was an unsolved math problem for a very, very, very long time. Wait, no, not the twin prime conjecture. It's something with number theory. It's not my favorite thing. But point being, I'm getting sidetracked. It's your guys' fault, not mine. These problems always have a way to cancel the h. There's always something you can do. So it might be just simplifying and canceling stuff. It might be having to multiply by conjugates. It might have to be finding common denominator. Something needs to be done. So work on it. Know that and if you don't get anywhere with what you're trying, that's okay. It's all right. I've thrown away so many pieces of paper in my life that are wrong. It's okay to be wrong and try again. So let's go ahead and do one of these problems. So find f prime of x for the function f of x is equal to x squared minus 3x plus 2. So if you want to, you are required to memorize this formula, the definition of the derivative. I'm not going to provide it. But what I can tell you is a surefire way to memorize it quickly is to always write it. Every single time you do a problem, no matter what, if it's on your homework or whatever, just write it every time. You will start to memorize it without fail. So f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Yep, it's the difference quotient. The only thing that's different is now we just add a limit as h approaches 0 in the front. And that limit sign will not get dropped, just like with every other limit we deal with. That limit sign will not get dropped until we're able to plug in h equals 0. So some students like to find f of x plus h off on the side. That's fine. I'm going to do that first, But as you get more and more comfortable, it might be in your best interest to do it as you work alongside. But I'm going to do it on the side right now. So f of x plus h is going to be the quantity x plus h squared minus 3 times the quantity x plus h plus 2. And we're going to have to FOIL this. We're going to have to simplify this. Sometimes you might want to, sometimes you don't. But I'm going to FOIL it out and get x squared plus 2xh plus h squared minus 3x minus 3h plus 2. When we FOIL it out, that's what we should get. So now I've found f of x plus h. So I'll plug that in for the first piece of the numerator, and then I'll subtract off f of x. This becomes the limit as h approaches 0 of x squared plus 2xh plus h squared minus 3x minus 3h plus 2 minus x squared minus 3x plus 2, all divided by h. Now, this is what John Doe student writes. And John Doe student has now just taken 1 year off of my life. Why? The minus f of x is here. But there is something that is where the issue is lying. What did John Doe student forget to do? He did not distribute the negative. That's right. Bad student. Bop him on the nose. If you're hanging out with, like, if you're working with other people, like if you're studying with other friends in this class, or if you see a student in like the tutoring room and they forget to do this, bop them on the nose. Just bad. Or just do the thing, like the thing we're supposed to do with dogs, like you jab them right behind the jaw, to nip at them, right? Do that. It's a surefire way to get kicked off campus. But point being, there needs to be parentheses here. The first one doesn't necessarily need the parentheses because it doesn't have anything, but this minus sign needs to get distributed. I see it happen every year, and every year I lose another year. Please don't make me die earlier. I now have a son that I have to take care of, so it's kind of important. Before then, but that minus sign needs to get distributed. And I know you're thinking now, you're like, Phil, you're dumb, stupid. You don't know what you're talking about. I know what I'm doing. I know everything. So I'll remember to distribute it. Probably will, but that's not guaranteeing that you can't account for everything else happening here, right? Somebody sneezes, or there's a fire bell ring, or someone gets up in the middle of the test, says, I can't do this, and runs out, which happened in a class when I was when I was an undergrad. Student just straight up said, I can't do this, and just sprinted out from the room. If that happens, you might forget that you were supposed to distribute that minus sign. So please, just put the parentheses there. It's 2 extra pen strokes. I know we don't want to get carpal tunnel, but it's important. So we got to distribute this minus sign. And what we end up with is the limit as h approaches 0 of x squared plus 2xh plus h squared minus 3x minus 3h plus 2 minus x squared plus 3x minus 2, all divided by h. That being said, by the way, if you feel comfortable skipping algebra, please be my guest. Please feel free to skip algebra wherever possible. I'm not testing on your algebra skills, I'm testing on your calculus skills. So it's okay if you want to skip a little bit of algebra here and there. But look at that. Isn't that nice? Isn't that nice? Those x squareds cancel. And oh, those 3x's cancel. That's fun. And those 2's cancel too. Huh. That's pretty cool. It just magically happened for us. That's pretty awesome. And so this becomes the limit as h approaches 0. Notice that I have not stopped writing my limit. because I haven't taken my limit yet. I have to write it down every single time. Yes, it's tedious. Just like putting, like doing the double space at the end of a sentence. Yes.
I just write like an equal sign, just so I don't have to write that in H here, like continuously down, equal, equal, equal.
How do you mean?
So like instead of writing movement H equals 0, just draw an arrow, just so I don't have to write it again.
Ah, I see. So a student, like writing this.
Um, Yeah, maybe you could write another.
Ooh. That's like saying ATM machine. It's still there because ATM machine, auto transaction machine. So it's not the same, but it's in the same vein of like, that hurts my brain, but I accept it. I accept it. But you have to write it. You have to write an arrow down. If you're not going to write the limit sign, you gotta have to write the.
I'll take it.
Okay. Yes.
They're like equal, and on the very end of the last step, I can limit as each approaches 0.
So another way to do it would be to take care of this algebra, like off on the side, and then just, so what you could do, if you don't want to write the limit every time, is you could take all this algebra that we've written and bring it over on the side here, and then once you've simplified it and canceled the H, then write the thingy right here.
Okay.
That's fine too. Who doesn't love writing limits? True. Okay. I got, like, fair enough. So I will accept that. That is an established rule between us now. Just so we're clear. That being said, if you take another instructor, they might not be as lenient on that. Okay. Just letting you know, in future math courses, if you have to write limit signs, they might get a little bit dicey. Like they might be a little bit upset, but I'm okay with it because I'm a cool guy. I'm a cool mom. If we all remember Mean Girls. All right. So everything else canceled. All those things up on the top, but the H hasn't canceled yet. But do we see something that we can do?
Yeah.
John Doe student says, "Oh yeah." John Doe student's wrong again, because John Doe student is trying to cancel a term. Can't cancel terms. You have to cancel factors. But we do see that these all have a common factor of H. Let's use blue. We haven't used blue. There's a common factor of H that can be pulled out front. And that cancels the H. Now I know I can take the limit. That's what the key fact is saying. We are not done simplifying until that H has been canceled. Yes, still.
I just crossed out the H, just minus, so it'd be like 2x plus H minus 3. I just crossed the H on all of it.
Yeah, that's fine. That's fine too. Like you can do, like, as long as you know that you're canceling out the factor of H, not a term of H. Does that make sense? So this then becomes the limit as H approaches 0 of 2x plus H minus 3. And now we can plug in the limit. So we're going to drop the limit sign, plug in H equals 0 and get 2x minus 3. And so that is f prime of x. Yes.
If you find the derivative of the way by just multiply, so for the first term, multiply by the power of 2 times x, which would be 2x, then drop the power, and then do minus 3 to drop the power by 1. So just be 2x minus 3.
Why? Why does that work? So we will learn that. We will learn that in a second. In section 2.2, we will learn the rules that make this a thing of the past. But as math students, we have to get ready to be hazed a lot. And so this is a requirement that we have to do it this way until we learn that thing. So every student has to do this once. And so Every student has to do a definition of the derivative problem on a quiz or an exam. Hint, hint, wink, wink. Everyone has to do a definition of the derivative problem. I'm not saying that there would be one on the exam. The definition of the, so
Like just solve.
so find the derivative using the definition of the derivative.
Oh,
So
Reading it.
that's not.
you get it? People watching the recording, I'm winking right now. So maybe make a note in your notes or something like that, that there might be something like this on the exam. Just saying. Just saying. Okay. Hector, sorry, did I interrupted you? What did you say?
No, not at all. No.
So next one. This one's dGdt. So I'm the reason why I do this, by the way, is that mathematicians, once again, have a bunch of notation that has no agreement anywhere. So I want you to be comfortable with all the notations. And remember, t is just a variable. So this is dGdt. It's the derivative of g with respect to t. So this is like g prime of t, or dGdt, is equal to the limit as h approaches 0 of g of t plus h minus g of t all over h. Write it every time. Write it every time. It's guaranteed way. You have a question? No.
I'm just confused.
Okay. For sure. Is like with the algebra that had to happen? For sure. We'll hopefully do another problem. Thank you for letting me know. I really appreciate that. Hopefully doing another problem will make it stick better. And if not, we'll go back to it. So on the side, I'm going to find g of t plus h. That's plugging in the value t plus h into the function. So that's going to be 1 over t plus h plus 3, or rewriting it 1 over t plus h plus 3 without the parentheses. Though if you wanted to just go straight to what I have written there, that's okay. So this is the limit as h approaches 0 of 1 over t plus h plus 3 minus 1 over t plus 3, all divided by h. And so that h in the denominator has not been canceled. And you would find out if you tried to plug in 0 right now that you'd get 0 over 0. Which means that there needs to be algebra done. What should I do? Take a second, don't answer. Don't answer it. Everyone get a chance to think about how we would approach this problem. So we need to simplify it somehow. Okay. Common denominator, is that what you can say?
Yeah.
Yeah, exactly. Sorry, I meant to, I saw you raise your hand first. My bad. But exactly right. Common denominator. Fair thought. Might work, might not. We don't know. Let's try. As we say in Sesame Street, I wonder, what if? Let's try. All right. So we'll multiply this one by t plus 3 over t plus 3. And this one by t plus h plus 3 over t plus h plus 3. By the way, I will say also, if you do watch my video on algebra that has to do with complex fractions, there are 2 ways we can deal with complex fractions. Complex fractions mean fractions within fractions. So this one has fractions in the numerator of a fraction. If you watch that video, or if you learned another way to take care of to simplify complex fractions, feel free to do it. This is just the standard way, but there is kind of a faster way, I think. But either way, when we do that, we get the limit as h approaches 0 of t plus 3 minus parentheses t plus h plus 3, all divided by t plus h plus 3 times t plus 3, all divided by, I'm going to make this line a little bit larger. Simplifies, this is the big bar over h. You could put the h in the denominator right from the get-go, and I encourage you to do that, but I'm gonna take that in one step. So this becomes the limit as h approaches 0 of t plus 3 minus t minus h minus 3, all divided by h times t plus h plus 3 times t plus 3. If you didn't believe me now, if you didn't believe me when I first mentioned it, hopefully you believe me now that the hardest part of calculus is the algebra. There's so much algebra going on here. So I want you to make sure you understand where everything came from. And if you don't see where everything came from, please let me know. That h is now in the denominator. There's only one denominator now, instead of having a denominator within the numerator and then the big denominator. I just move that h by doing, this is h over 1, so I flip and multiply it and multiply it by this, and that's why the h is now down in the bottom. So, isn't that nice? The t's cancel, and so do the 3's. How pretty. Limit as h approaches 0 of negative h divided by, and then once again, I'm being way too over the top with my algebra. I'm doing every step. If you feel comfortable skipping steps, please feel free to do so. Negative h divided by h times t plus h plus 3 times t plus 3. And then the h's can cancel. And we're just left with a -1 up in the numerator. And now we can plug in h equals 0. Once we've canceled that h in the denominator, that original one, you know you've done enough. And now you can drop the limit sign, plug in h equals 0, and get our answer, which is going to be -1 over t plus 0 plus 3 times t plus 3. But that's t plus 3 squared. So that's going to be the dg dt, the derivative, dg dt, is equal to -1 over t plus 3 squared. That's fair. That's fair notability. That did not look like a square. You could leave it as -1 over t plus 0 plus 3 over times t plus 3. I wouldn't be too upset about it, but I'd like you to simplify it. Good. Any place where there's arithmetic, feel free to skip it if you feel comfortable. But it's not required. All right. Any questions on that one? Is that helping a little bit, or do you need a little more? So, yes, it is something that we definitely need to practice plenty. We can do this one too. dy dx. Oh, yeah, you need a second. Oh, thank you for letting me know. We got a square root. Square root this time. Maybe I'm alone here. I find this to be very soothing. I find just canceling of factors and stuff. It's very, very fun to just take an expression and just kind of mess with it. It's like Legos. You just kind of start with 2 pieces and see where things go with you. Just let your imagination run wild. But in a structured manner. It has to be structured. No fun. It has to have, you know, like my brother was very, very particular about Legos. I didn't care too much, but he had like the wings had to be the same color on his spaceships. I was fine with it being one red, one blue. But either way. All right. I wanted to bring this one up, and there's a reason why I wrote it as y equals the square root of 3x minus 4. Because when we see functions in this way, we forget that y is representing a function. So you can write this as y of x is equal to the square root of 3x minus 4. We forget this fact, that we can just write it that way. It's y of x, but we tend to write it just as y. So dy dx, find the derivative. So dy dx is equal to the limit as h approaches 0 of y of x plus h minus y of x all over h. I'm telling you, if you write it every single time, you will memorize it without even having to try. Memorize it without even having to try. If you always write it down with a problem, it's a guaranteed way to, it's just one extra way that you can help your mind learn it faster. So then this becomes the limit. And this time I'm going to do it all in one step. I'm not going to find y of x plus h off on the side. You're more than welcome to do that. It's fine to do so, but I'm going to do it as I go along. So this becomes the limit as h approaches 0 of the square root of 3 times x plus h minus 4 minus the square root of 3x minus 4, all divided by h. And you could simplify the inside of that to be 3x plus 3h minus 4. That's fine too. And in fact, I would recommend it. How do I do it? Take a second. Get a chance to think about how would I take care of this monstrosity? Yes.
The conjugate.
The conjugate. Very, very good. Whenever you see square roots, we always think, I don't like dealing with that. I don't like that. Let's try and get rid of it. So we'll multiply by the conjugate. Square root of 3 times x plus h plus 3 minus the square root of 3x minus 4 divided by square root of 3 times x plus h plus 3. Whoa. Where did that come from? That's supposed to be a minus 4. I don't know what happened there. And that, what am I doing? Plus sign. Sorry about that. Yes. Square root of 3 times 1x plus h minus 4 plus. Sorry about that. It should be plus. There, that's the conjugate. That should be the opposite sign. And then square root of 3x minus 4. And if you want to be strapped for time, you could put like just quotation marks as well. It's okay. But by doing that, yes, we could FOIL it out. But you don't have to. Remember, because this is that thing. A plus b times a minus b. That like gives you a squared minus b squared. So by multiplying by the conjugate, it's just going to get rid of those square roots in the numerator. So this becomes the limit as h approaches 0 of 3x plus 3h minus 4 minus parenthesis 3x minus 4, all divided by h times the quantity, square root of 3x plus 3h minus 4 plus the square root of 3x minus 4. A lot of algebra. So much algebra. I love doing algebra. Yes, distribute the negative. So just as a little aside on what I've done here is I distributed the 3 into the x plus h in every situation. So I distributed the 3 here. That's why I've got the 3x plus 3h minus 4 after squaring it. And the same thing with the denominator, just to make it nicer. And so we can cancel stuff. The minus sign will get distributed. And just to save on space, that'll cancel the 3 x's. The minus 4 minus the negative 4, those will cancel. And we'll have the limit as h approaches 0 of 3h divided by h times the square root 3x plus 3h minus 4 plus the square root of 3x minus 4. And now the h's cancel. Oh, goody, goody. It's almost like that's designed to happen every time. It's pretty miraculous. Every single problem you'll encounter in this course, there's a way for that h to cancel. Some way, somehow, that h will cancel. So if you haven't figured it out yet, Just keep trying something new. And so now that the h has been canceled, I could plug in 0 for h and drop the limit sign. And write that this is going to be 3 divided by the square root of 3x minus 4 plus the square root of 3x minus 4. And so, oh, yes. Go.
What happened at the bottom? I thought it was x plus h. I didn't found 3x plus 3h.
By distribution. So I distributed the 3 in to the x and the h.
Oh,
So 3x plus 3h. And that was just so that it would be easier to deal with in the numerator, but either way. Now these things do not cancel the square root. These are like radicals, kind of like terms. So this simplifies to dy dx. Dx is equal to 3 over 2 square root 3x minus 4. Max, yes.
Square root of 3x plus 3h minus 4 plus square root of 3x minus 4 square root of 3x minus 4.
So how did I get from this step to this step? So notice that I've dropped the limit sign because I'm going to take the limit by plugging in h equals 0. So this becomes 3x plus 0 minus 4, or just 3x minus 4. And then this thing, there's no h's in it, so it stays there. And then this h was gone because canceled it, so that's why I've got the 3 up there. No, not your bad at all. That's a good question. So hopefully taking the derivative by the definition, it's something that you just need to practice every once in a while. Doing the algebra off on the side, I always like, so we haven't taken a test in my class yet. We haven't taken an exam. I always have an extra sheet, an extra page at the very end of the exam that you can rip off for scratch paper. Please use it for any little minor calculations that you want to do that you're worried about, like being wrong, whatever it is. I give you scratch paper, and I will have plenty more if you need it. So if you want to do those calculations off on the side, go right ahead and do so. So key fact number 2 is that how do I want to write this? The derivative gives the slope of the tangent line at any given value of x. So the derivative is a function, just like the original function. The derivative is a function itself. But when you plug in a value into the derivative, it represents the slope, and like it's equal to the slope of the line tangent to that curve at that x value, which is exactly by its construction. If we go back to that picture we had up here, this right here, if I were to compute the limit as x approached, the limit as x or h approaches 0 of f of a plus h minus f of a divided by h, that would give me the slope of this line, because it's taking the secant lines. This essentially is the secant line that I'm making get infinitely closer and closer together. And so when you plug in a specific value into the derivative, you get the slope of a line tangent to the curve at that value. So in the interest of time, saving on a little bit of time. So it says for f of x equals 3x squared plus 1, find f prime of 1 by the definition. I'm going to, actually, no, by the definition. That's what I wanted you to do. Then write the equation of the tangent line. So does everyone remember the 2 forms of a line? So there's slope intercept, y equals mx plus b, right? And then there's point slope. Y minus y sub 1 is equal to m times x minus x sub 1, right? Point slope is your best friend. Point slope is the way I want you to write your lines, your tangent lines. I always want them written as point slope form. Point slope form is just infinitely better. And we'll talk about why in just a moment. But in the interest of time, we're gonna skip doing this and find f prime of like. So f prime of x is equal to 6x. Just letting you guys know, we will find a faster way to prove that in a little bit. But f prime of x is equal to 6x. So f prime of 1 is equal to 6 times 1, or just 6. You could just write 6 and it'd be fine. That is the slope of the tangent line, which I denote m sub tan. So this is m sub tan. So f prime of 1 is the slope of the line tangent to the curve of f at x equals 1. So if I were to draw this curve, by the way, so like just, you don't need to draw this, but 3x squared plus 1, that's a parabola shifted up 1 unit and vertically stretched by a factor of 3. It looks like this, right? And here, let's just say here's 1. Now my graph is not drawn to scale at all, but if I were to draw the line tangent to this curve, if I were to draw this curve just by rough sketch, this would have a slope of 6. That's what this is telling us. So when you plug in 1 into the derivative, it gives you the slope of this line. So we have the slope. What do we need for the equation of a line? We either need 2 points on the line, or we need the slope and a point. We're not given a point. Oh no. What do we do? How do we find a point on the curve? Use the value. We said find the equation of the line tangent to the curve, or the tangent line to f at x equals 1. So we need the point. Need a point on f. Well, if x equals 1, f of x, then f of 1 is equal to 3 times 1 squared plus 1. Now, I know you could do that calculation in your head. Sure, fine, no big deal. The reason why I'm writing it out in particular is to remind us that this is the function, not the derivative. We're not plugging this value into the derivative. We plugged x equals 1 into the derivative to find the slope, but to find the point on the curve, f itself, find the point on the curve f, we have to plug it into the original function. So, and that will be 4. And so, to clarify why I'm being very, very particular, it's very, very easy to get these two things mixed up. They look almost identical. It could just be a little smudge on your paper and you think that you're writing the derivative. So just be clear, f versus f prime. If you want to write dx, dy dx instead, or df dx, that's fine. But so this means we have the point 1, 4. So we have our slope, we have our points, so we can create our line. So y minus y sub 1, so y minus 4 equals m, which is 6, times x minus x sub 1, which is 1. Or y equals 6x minus 6 plus 4, so minus 2. So we found the slope, and then we found the point by plugging in the x value into the original function. And then we could use that to use point slope form, or you could solve for b by doing the y equals mx plus b situation. Now, I will say, I think that the slope and the point slope form is infinitely better. And it's because, first off, you can always get slope-intercept form from point-slope form by just simplifying it. That's exactly how I found this. I distributed the 6, add the 4, that's where I got that. The other reason why I like point-slope form more is because this tells you where you're drawing the tangent line. By it showing this -1, this is -1, it's saying that we're looking at the tangent line at 1, 4. So that's the reason why I like point-slope form more. It tells us more information. It tells us where the tangent line is going to happen. But either way, like when it comes to like computations and stuff, then this is where that becomes a little more useful. But either way. All right. The derivative of y equals x cubed minus 2x plus 5 is y prime equals 3x squared minus 2. We can use this without proof. Though if you want to have a great time this weekend, buddies, highly recommend it. It's a good one. You get to practice foiling out a trinomial, right? Do an x plus h 3 times. It'll be a blast. I really recommend it. Determine the equation of the line tangent curve at the point 2, 9. So this time we're given the point. So point's already given. Just need the slope. The point given, point taken. And you'll notice if you plug in 2 into the original function, so 8 minus 4 is 4 plus 5 is 9. So this is coming from the original function, not the derivative. The derivative is used for the slope only. The point is found from the function itself. So y prime of 2, because that's the x value, right? We want to know the derivative at 2. We're talking about the point 2, 9. So y prime of 2 would be 3 times 2 squared minus 2. That's going to be 3 times 4. So 12 minus 2, that's 10. And that is our m-tan. So that means we have y minus 9 equals m, 10, times x minus 2. Or y equals 10x minus 20 plus 9 is minus 11. I write it in both forms, by the way, because if you're going to have to do something with the tangent line, it's better to have it in slope-intercept form. So that it's y on one side, x is on the other. Or like x and all the other algebra stuff on the right-hand side. But if you're just asked to find the equation of the tangent line, I really recommend just writing point-slope form, because then you don't have to do any algebra. You don't have to do anything else besides just plug and jump.
So one is point slope, the other is what?
Slope-intercept. So this is slope-intercept form, where your slope is given and this is your y-intercept. This is point-slope form because it has your slope and then the point that you're using to create the line. Yes, Steve.
Like one, you're given a negative number for point slope form, you just switch your sign, right?
Yep, because it'd be like so if this had been instead of 2, 9, if it had been -2, if it had been -2, 9, then this would become minus and -2, which would become +2. Yes.
So if you're ready for the slope, you can show that the slope is on both sides.
Yes. So you can like that's the whole reason why I like slope-intercept form so much more, point-slope form so much more, because it gives you slope-intercept form immediately just by doing a small arithmetic. All right. Any questions so far? There's a lot of information today, by the way. There's a lot of information. And I'm sorry that we didn't get to take a break today. Normally I try to give at least a 10-minute break. Sorry, but today is not one of those days. the derivative of the function f of x equals 1/3 x cubed minus x squared minus 7x plus 2 is f prime of x equals x squared minus 7 by minus 2x minus 7. We're gonna use this without proof, but if you want to get some good practice, go ahead and crack open a cold Mountain Dew with your friends and bust this one out. Yes. Like the proof of it? No,
This be only.
no, like we're gonna go through this one here. Absolutely. I'm just saying if you want to find the derivative by hand instead of being given it, feel free to. Like it's an extra practice problem of using the definition of the derivative. Determine the points where f has a tangent line with a slope of 8. Okay. How would I do this? Yes, please.
And then once you solve it, you can factor out and then get the x values, and then plug in the x values in the original equation to get y values.
Very, very, very good. That's the entire process listed out. So we want the tangent lines to have a slope of 8. The derivative gives us the slope. So if we want m tan to equal 8, that implies we want f prime of x to equal 8. So we've got an equation that we can set up. So f prime is given to us. It's x squared minus 2x minus 7 is equal to 8. And we can solve that in any different way we want. But bring the 8 over. So just to kind of reiterate while people are writing this down, the whole thing that we're like, the biggest crux of this situation is that we want the tangent lines to have a slope of 8. The derivative gives you the slope of the tangent line at any given x side. So if we want the slope to be equal to 8, we will set the derivative equal to 8. And then we solve that equation. I'll subtract 8 from both sides, get x squared minus 2x minus 15 is equal to 0. And that factors nicely. I try to make sure things factor nicely wherever possible, but remember we always have our handy dandy quadratic formula as well, right? We all remember the quadratic formula? Okay, I'll sing it once. Sing it once, and that's it. I'm not going to do the Irish dance when I'm doing it. So just as a reminder about the quadratic formula. So if you have ax squared plus bx plus c equals 0, you can find the solution to any quadratic using the quadratic formula. You can factor it. Usually that's the best way. It's faster. You don't have to deal with anything. But if you want to use the quadratic formula, I'm saying it once. And that's it. You can't ask me for it again. X equals negative b plus or minus the square root b squared minus 4ac all over 2a. It's one of my son's songs for bedtime. I'm not lying. He likes it. So that's the quadratic formula. That's the quadratic formula. You can use that to solve these things as well. But always try and factor it by hand if possible. It's quick. It's usually quicker than having to deal with that. So x plus 5, nope, not plus 5, x plus 3 times x minus 5, 0. That gives us x equals negative 3 and positive 5. So, but this gets to the last part of what Capri was mentioning, is we need to plug these values into the original function because it says determine the points, the coordinate points, not just the x values. So always read the question carefully. If I asked you just find the x values, you'd be done. But I asked you to find the points, the coordinate points, because I really want to hammer this. When we're finding the points on the curve, we use the function because that's how you would find points on the function. If we're finding slope, that's the only time we use the derivative. So f of negative 3 is going to equal, someone has my calculator. Thank you. I do not know this off the top of my head. I've actually forgotten my notes today. So we're going a blind run. So 1/3 times -3 raised to the third power. If someone can find plugging in 5 at the same time, that would be great. Not required. I can manage.
Can you repeat that again? Sorry.
Just plugging in, like finding the f of 5 as well.
I'll just plug in -3.
Yeah, plugging in 5 into f of x. So I get 5 for the first one. So that gives me the point -3 comma 5, and then f of 5 is going to equal. Let me get it. -49/3. -49/3. Boom. So 5 comma -49/3. That's a horrible handwriting there, so let's write that better. -49/3. Still terrible, but better. Boom. Those are the 2 points on the curve that have a slope, a tangent line with a slope of 8.
Well, that's good.
That's the answer. So to reiterate, as like Capri said it perfectly, if we wanted the tangent lines to have a slope of 8, we want the derivative to equal 8. We solve that equation, we get some x values, but since the question is asking for the points, we have to plug them into the original function to find the other part. Oh wow, we're out of time. Okay, well, that'll do it for today. So please go over that exam review this weekend. Our exam is next Wednesday. Yeah, this coming Wednesday. So a week from today is our first exam. Study up. If you have any questions, feel free to email me. Otherwise, you guys have a great rest of your day, a great weekend, and I'll see you on Monday, okay?